Okay, it's 10:30, so let's start. Let me take off the mask. This is lecture 9 for CIS6395, and we will finish the example, and then the remaining time we will do this. This is like a, well, it's not a real case study, but it's like a cyber competition contest. They provide this kind of competition question, and so it's more realistic than the normal examples. So this one basically tell you how you can do analysis, forensic analysis on network trace by yourself. So let's first finish the Wireshark example slide we start last time. I think the first example, we only collect the data, but we haven't had time to analyze the traffic yet. Basically collect the Nmap stick on Wireshark, on the Kali Linux, and then we can analyze the traffic. But my last time I didn't save that captured Nmap traffic, so I need to do the capture again. So first, I need to find the two Windows machines. They can see each other. So this is the IP config for the Windows is 2.15. For the Kali Linux, I have config as let me make it bigger. It's 2.4. So remember last time I have already opened the echo request, echo response service on the Windows VM firewall. So now, I should not ping itself. Ping should ping that the Windows machine. So we can see that the ping can go through the Windows machine is 2.15. Yes. So now we can use Nmap. Suppose we just do this fast scan, 10.0.2.15. But before we actually start the scan, we run Wireshark. On the Kali Linux VM, the default network interface is Ethernet 0. So you just start capture, and normally, the Kali Linux is very required. There's no background networking application just connecting to the internet. Well, there's still some, but not that many. Now we can start the Nmap scan. So this scan finished, and now we can stop the traffic capturing. Let's save. Let me save this trace first. Otherwise, Nmap traffic. Okay, so you can see this Nmap scan. It scanned 100 port. So that's the fastest scan. Only scan 100 port. Normally, it will scan 1,000 port. So you should not try Nmap on internet target, because Nmap has very, very clear signature. So any network manager, they will see that some IP from your place is scanning their network. Even though this happened a lot in the real world, but it's still not a good thing. So don't use Nmap to scan a real target. Just use it to scan your own virtual machine or scan your home computers. For example, when you set up this virtual machine at home, you can set up in the bridge adapter network mode. Then your Kali Linux will be able to be in the same local area network as your home computers, like your smartphone and iPad. Then you can use Nmap to scan your home computer and home like all the smart device. Okay, so let's analyze this. So overall, it's a 224 packet, and you can see, you can see that Nmap actually starts when we do here. The first several packets, remember when before I start Nmap, this first 7 packet is captured. This is like ARP protocol. ARP protocol, as I mentioned in the introduction, is basically the protocol only exists in a local area network where each device try to find what other computer device, their IP address or MAC address exists in the local area network. So ARP traffic appear allowed in the local area network only. It will never go out of the local area network. This is ICMP version 6. So that is IPv6 stuff. Okay, so the actual Nmap starts from here. The first, this is my Kali Linux IP address. The first is try to do a DNS query for that 10.0.2.15. What's the domain name for that computer? So basically, Nmap, even though you give an IP address for it to scan, it also do a DNS query, try to find what's the domain name. You can use Nmap to scan a domain name. Then Nmap will do DNS query to find what's the IP address for that domain name. So anyway, it will do a domain name query. So this is a standard query is a PR record. PR record basically find what it's a reverse DNS lookup. Normally, DNS lookup is what's the IP address for a given domain name. This reverse DNS lookup is what's the domain name for this IP address. So that's called reverse DNS lookup. So this is a DNS query, and it does DNS query 2 times. I don't know why but anyway, it do DNS query 2 times, and then it do a query to another DNS. Why does it do DNS query to this 192.168.1.254? I'm not sure. This should be the 10. And this DNS server, because this local DNS server, remember the local where my computer is set in the network mode, then the VirtualBox will create a virtual router for this local area network. So this DNS server is use that local router. So this is like a virtual local router created by VirtualBox, and this one. But I'm not sure why it generates this query to 192.168 to this one. And so this virtual DNS server by the VirtualBox gave the answer. So give the answer that this what's that computer domain name? No such name, because that Windows VM, we actually don't have a domain name for that. So anyway, now it start to do the scan. You can see this is from this source port, because this is the Windows VM IP address 2.15. It find out to connect to 135, it's a SYN packet. Then it send to port 80 is also a SYN packet. And let me make it bigger. So you can see that this is a SYN packet to 53, SYN packet to 110, SYN packet to 113. So basically, it's trying to do TCP connection request to all these 100 preset ports. So these are 100 preset ports. They are the most popular port for any attacker to attack. So those are the pre-configured 100 port. We know that port 53 is DNS. This port 80 is HTTP. 135 is a network neighborhood used by Windows machine. So that is a highly possible attack target. And it also scans some higher number of ports. These ports are some network program, for example, some computer game, some networking software. They will use those high port. So these so you can see that all these is a SYN packet. So it sends out a lot of SYN packet to all these ports. That's why this traffic can easily to see that it's an nmap scan because you can receive a large quantity of SYN requests from a single IP address. You can see from the single source IP address and to all these ports and try to get response. So this is a SYN packet. It's 100. And it actually sends SYN request to the same port twice. You can see this. Sometimes they are connected. They are consecutive. Sometimes they are distanced by a few packets. Like this one is 5666. This one is also 5666. So it actually sends SYN request to every port twice. That's why we have this 224 packet. Even though it's just a SYN request to 100 port, but for every port it's sent twice, because it tries to make sure that if one of the SYN requests is dropped because of network congestion, we can still have a SYN request reached by the destination server. So for every one, it sends 2. So some of them they are together. Some of them they are deferred by some distance. Like a 554. This is 554. This is 6001, 6001. So every port will do that. So if we check TCP like SYN equal to 1. This is wrong. TCP flags dot SYN equal to 1. Then you can see that all this SYN packet. And if a port is open on the target server, target will respond with a SYN-ACK packet. Remember, that's the TCP connection request, the server's response, SYN-ACK. So if we want to find that packet, then we should use and TCP.flags.ACK equal to 1. So basically, we try to display any packet that has both SYN bit and ACK bit set as 1. And so here is nothing. Let's see if we see this nmap scan. You can see that none of the port is open. So that's why there is no service port give you this SYN-ACK response, because right now my Windows 10 virtual machine, the firewall is still active, so it has blocked all those ports to the service. So there is no SYN-ACK packet. There is no open port. If there is a port open, it will respond with a SYN-ACK packet. So if we just check TCP.flags SYN, and you can see there are displayed is 200 packets, exactly double the amount of 100 port, because the source sent 2 SYN packets to every port. So it scanned 100 ports. So there are 200 SYN request packets. Okay, so if we open another computer virtual machine like this one, because I want to show an example that actually have SYN-ACK response. So this is Metasploitable Linux. It opened a lot of service port. MSF admin. The password is also MSF admin. Okay, so I first find what the IP address is 2.5. So let me do this scan 2.5. But before I do the scan, I restart this capturing, and I do 2.5. And now I stop the capturing. You can see that when I scan the Metasploitable Linux, these are the open port for that Metasploitable Linux VM. So that VM opened a lot of service. It also scanned, so it showed that the 82 port, they are closed. So 18 port here, they are open. So if you come back to this one, it just means that if you find tcp.flags.ack equal to 1, then you can find that these port 21 port respond with a SYNACK. So that means the target machine, the 21 port TCP 21 port is open. So we can see there are 18 packets here because 18 port is opening that. Okay, so that is an example for this checking the program running on your own computer to see its behavior, network behavior. You can use this way to do that. So the next two examples, they are actually from this Don Song's class. So first, you use this Q1.pcap. This traffic trace, this scenario is that it captures the unencrypted Facebook traffic. So in the old days, Facebook still has unencrypted channel available for users. But of course, right now you cannot log into Facebook without using HTTPS anymore. But in older days, in the beginning, Facebook support HTTP traffic. Then it makes it possible for you to use Wireshark or other soft network application to capture the traffic. This one shows that someone impersonated as you and posted, or someone impersonated as your friend and posted message to you. So that is the example. So let me open that question 1 trace. Find out this impersonate message and find out what's the post. And how does attacker impersonate as your friend? Because each user is identified by it's like a cookie value. In Facebook is this C user field. So every user has a unique ID in that. The attacker posts the message using the C user as your friend. Then your program will treat it as a post by your friend. So you should check the HTTP post query and check this cookie value, this C user cookie value. In Wireshark, there is one powerful operator. It's called a keyword called contains. So this keyword basically find any packet that actually, this operator basically find any packet that actually contain a specific keyword in it. Of course, this keyword is capital sensitive. So capital letter, small letter, you need to make exactly match. So this is a very powerful operator in Wireshark. because the question said that this is HTTP traffic. So if you want to see HTTP, you can directly see it. And so here is get and the post. The post is basically your web browser connect to the Facebook and post something. So contains C user. So HTTP contains the keyword is C user. Then it will display all the message, HTTP message that actually contain that specific keyword. So then you can manually go through these to find the user information. Like if you see here, this is a HTTP GET message, and where is the C user? If you open this cookie value, so you can see this cookie value. This is one of the cookie value. Many websites use cookie to uniquely identify a remote browser, for example. So this is that C user's cookie. It's 42500, and this is also 42500. So you can see that the IP address, there are something different because this IP address is 0.4 and from this user, but there's another IP address. It also uses the same C user. Because this is get command, so this 151.89, it must be the Facebook server. So this should be the client. But you can see from the trace that from two different IP addresses, the two different IP addresses, they are using the same exactly C user cookie value. So one of the IP address must be attackers impersonate as the real user. So that's the first thing you can discover. This is a normal post, and well, you can check each IP address to find whether which one is normal, which one is not. But the most post is from this 10.024. So this is a normal post, but from time to time there is one post from this IP address. There's still a lot. So if you don't know which one is the real one, you need to inspect each IP address post message to see which one is normal, which one is not. But you can go through basically, for example, because these are all TCP connection. So you can click the packet, then using this follow TCP stream, or maybe using follow HTTP stream is good. But follow TCP stream, and you can see the back and forth between these two users. Well, there are a lot of back and forth between these two users. Oh, it's the TCP stream equal to that. Let me see how to finalize this one. And here, post message, the hint is that it's in the HTTP post request. So we should find HTTP post request. So now, remember, we have focused on this specific TCP connection, and we should focus on HTTP request equal to post. No, it's not. HTTP. Oh, one way is that you can use contains post. So that's easy. As long as the keyword post appeared in that packet, it satisfies this filter. So we use this one. And now we can see all the post message from this specific IP address. And because the Wireshark understood HTTP protocol, so it can reconstruct the content in the packet. So you can see this first packet, it showed the content, this HTML from URL encoded, because it understands that encoding method. So it showed that post. Because there are only a few packets, so you can go through each one by one. And what's this? User host. In which field? Server's response. Oh, sorry, I think I forgot which message. It actually host.
Professor?
Yes.
In the PowerPoint, it says that 192.168.121.185 IP is the normal post, and we're looking for
it's normal
10.04.
Oh, sorry. Yes, you're right. Thank you for pointing out. Yeah, I showed the TCP stream of this normal post one, but I couldn't find the message. So, thank you. Let me go back, clear this, and find this 10.4. Anyone and follow TCP stream. Okay. Let me see. No. Okay, so this I use IP address is this one, basically the other client, and as I moved the HTTP contains a post. So this is the one, and this one actually has this message, this HPC message. So these are the message. Let me see. Yes, so that is a message. Why it's not in that TCP stream, I'm not sure. Let me see why it is not in that TCP stream. Maybe from 10.0.0.4, it has two TCP streams related to its connection. So in one TCP stream, there's no such host. So if we use this TCP stream and HTTP contains host, so it showed one. But this is TCP stream 127. Probably, I think that is in a different TCP stream. That's why. So this one contains that message, but let me follow TCP stream to see it's string 7. Oh, it is a string 127. And HTTP contains host. Oh, it actually has. Okay. So my operation is correct. So you can first of all, you can either using the TCP stream, follow TCP stream, then you further refine any post message in it, or you can just put IP address. Suppose you specify that particular IP address is attacker's IP address. You can use IP.address equal to that particular IP address to do this. If you don't know which one is, suppose you find any HTTP post message, we can see that there are a lot of post messages, but they are unrelated. They are not to this Facebook server one. Because we only find the post that has this keyword that is related to Facebook, because the trace has many other web connections. They have this post message. So only use post may not be good enough. Okay. Anyway, for this one needs some pre-knowledge. The pre-knowledge, of course, the hint can tell you that you need to search for C user. You need to check the post message. And remember to use this contains keyword, because this contains operator is very powerful thing for you to find any keyword in the traffic. The second question is to analyze this Q2 question 2 trace. This trace is a little bit large, it's more than 86,000 packets. This second question asks you to analyze HTTP web traffic. And of course, we only analyze HTTP traffic, not HTTPS. HTTPS is encrypted, so there's not much information. You can analyze that. The question is that there was a leakage of a file through this web traffic, and determine the type of attack used to access a file, and what was the file name. How do you know it was successfully accessed? So that's the question. So first, check HTTP traffic. Actually, you can find many URL requests that connecting to this. Let me close question 1. So if you don't know what's the attack, you first, because it asks you to find web traffic, so you first use HTTP filter to filter out. it will still display more than 2,000 packets. So it's still a lot of packets for you to actually analyze. If you don't know where to start, you can quickly glance through this summary of the HTTP traffic to see if there is any abnormal things. Oh, this HTTP 1.1 not modified. This is the normal web server response. Because if you visit a website in a closed time, the first time you visit, you get all the image text object from the server. The second time when you visit the same web server, your web browser probably does not need to download all these image objects again, because your web browser already have the cache in its in the browser program. So the web server will most likely give you this response saying that this particular object is not modified since your last visit. Because when the browser sends the request to that object, the browser will have a field value saying that whether this object has been modified since which time. If the object on the server, if the object has not been modified since that time, the server will basically give you this not modified response. So this is normal response. And we can go through, and there are some longer URL, so this seems to be fine. And you can go through and, well, clearly from here, there is something wrong because this is HTTP GET. So normally this is fine. But what about this? This is a // because in many web servers, they are in web server, the URL, you can have the path information, right? So this is // that means you go to the parent folder to get the object. So if you have one // or two // maybe that's normal because some URL they use this relative path information in the URL. But you have so many // so that's clearly abnormal. And in addition, you can see what it's trying to get. Get is etc password. So etc password is a password file on the Linux machine. So clearly that's not a normal URL. Normal URL should never get a password on the web server. So clearly these are the attack packet. And attacker, they're all from the same source, this .61 IP address, and using different level of this // because attacker does not know what's the relative address, what's the relative path location between the current web page directory to the root directory on the remote Linux server. So attacker could send a lot of these requests with different level of this // hoping that it can reach the actual target. So if now we know that the attack actually because of this kind of attack, so we can find those type of abnormal requests. If we only want to show those abnormal requests, you can use HTTP contains this to just show those traffic. Because there are 2,000, these are normal HTTP requests, so we don't care about that. So we can just use this operator contains // well, these are normal things. Why these have this // in it? Oh, because in some normal URL link, they have some // in them. Maybe if we don't want to display this normal packet, we can put another // so now we can see these are all wrong packet. This is GET. This is response from the web server respond to the connection to the client that the object not found. because most of this get command, clearly you're not getting the real object from the web server. The web server will give you the HTTP not found. You can see this HTTP not found response. Use this, we can find out what file the attacker tried to get. We can find that, well, these try to get the etc password. And here, this is attacker try to get this chat.pdf file. You can see using 2 level, using 3 level, using 4 level, 5 level. So attacker just to try different relative directory location, try to get this second file. And you can see this get this second file. So there are 2 files attacker try to get, etc password and the shader. So which file has attacker been successful? You can use, for example, follow TCP stream to follow that, or let me see. Is the shader successful? You can. How do we find that whether this connection is successful? Well, we want to find the response from the web server to the client on that particular connection. Suppose we want to find the response. HTTP contains the chatter. What's that file name? Chat CIS6395.pdf. We just find all the HTTP traffic that contain this keyword, chat.pdf, and try to see if there is any response that is like 200 OK response. We can say, and HTTP contains like 200 OK message. Well, we find one. This one contains this 200 keyword. This packet also contains this chat.pdf keyword. And this is HTTP response 200 OK. So that means the server actually respond with the file. We can see this hypertext. You can see this packet. This is the request, the URL, and this is the file, and the data part is actually that chat.pdf. So now we know that attacker have got this chat.pdf successfully. If you want to find whether attacker get this password file successfully, you can use this to find that, well, actually attacker haven't got the etc password file successfully because there's no 200 OK response from web server that contain this password keyword. So now we have found the answer that attacker successfully get this PDF file. And how do we obtain this PDF file from the trace? You can use, since it belongs to HTTP, we can use HTTP, this export object, to check all the objects in the HTTP traffic. We can use export object HTTP. We can see all the objects from the connection. There are too many, because this is a very big trace. So there are too many to see content type text filter. Let me see CIS6395.pdf. And you can see that, well, these are the packet number. So all these packet contains some section of this PDF file, because this PDF file is large, so it was transmitted by a sequence of packets. So these are all the sequence of packets. If we export each one, that's not enough because it's just maybe a single packet. Like this one only has 1 kilobyte, so clearly that's not good enough. So this Wireshark extraction. Let me see if there's any information. This Wireshark extraction is not good enough because it doesn't put all these small pieces of the PDF file together. But let me see. Well, actually, this is a size. This one actually is correct because the previously you can see all these are just 100 bytes, 200 bytes. So that's just the data contained in each packet. But this one, it showed application is 22 kilobytes. So 22 kilobytes is probably the Wireshark get last packet, then it combined all these previous packets together and composed that single PDF. So if this looks real, let's save this one. Let's save as PDF. Now, let me open this one. So this is 22 kilobytes, and this one can be opened. So this is the complete PDF file. So basically, so this is a file that is stolen by the attacker. Basically, in the Wireshark for that export object, for all the previous packets, it only contains that fraction, only that packet content for that PDF. But the last packet, until the last packet, Wireshark will be able to reconstruct the PDF, put all these packet content together to get that PDF file. So, any question for this question 2, Trace? Okay, so that's the example. So now we introduce a more realistic example, which is this network forensic puzzle. Originally, this is from this forensiccontest.com. Forensic Contest is like a cyber competition service. They from time to time they will do this open competition. So this is one of the puzzle published in 2009. So it's very long time ago. But so like last year, this post is still on its website, but this year I couldn't find original content for this puzzle. Here is a YouTube video I found yesterday. Someone solved this puzzle using demonstration, but it's there's no words, so it's just a silent video. And this puzzle has been explained in detail by this network forensic book. And I used some slides from this network forensic book. as well for this puzzle. But basically, this is this forensic context puzzle. Give you this more or less realistic scenario that a small company suspect that one of their employee and is transmitting some secret information like a secret recipe from this company's network to an outside attacker. So the his computer, her computer has been monitored. The network traffic has been monitored, and now the security staff try to analyze the network trace to find out whether Anne has actually leaked some company secret information and what file has been transferred out by Anne's computer. And whether this, because you have to reconstruct the file to see whether this is a serious leak or not serious leak. Unexpected laptop briefly appeared on the company's Wi-Fi network. The Anne's computer, suppose Anne's computer is this IP address. It sent AOL message over the Wi-Fi link to that unknown computer appeared in the internet, appeared in the Wi-Fi network. So you try to analyze this trace to try to answer these questions. So this is the entire information for that puzzle. The puzzle gives you this description, give you this network trace, and ask you to answer this question within, for example, 24 hours. And of course, you not only answer it, but also give how do you derive the answer. Then after one day, they will try to say which is the first one, which is the second one, give you this computation result. From this problem description, we know that we should check traffic from this Anne's computer, from this particular IP address, and also we should check AOL message. So let me open that file. You can download the file from this from here. So let me. Okay, so this is not a big forensic file. It only has 240 packets. You can basically manually going through them. But from the protocol part, you cannot see any AOL. It's just the TCP and like SSL. SSL should be is a secure traffic used by HTTPS. They are supposed to be encrypted. You cannot see the content. When you open this file, and the question one asks you what is the name of Anne's IM body. The question asks you for AOL message. The parcel's name is called AIM. So we need to find the AOL instant messenger message. First, remember we need to focus on the Anne's computer. So you can use IP address, put this Anne's IP address in the future, just to focus on Anne's. So here it doesn't specify the source or destination. So both direction traffic related to Anne's computer we will show. And here is just a TCP. TCP is just an acknowledgement. The data content is SSL. So SSL is supposed to be encrypted. If it's actually SSL encryption, then we cannot do that much because it's encrypted. But if you check any of this, you can see this actual things here, actual data here. You can actually see some English text. So clearly, even though it shows SSL protocol, but this traffic is not really encrypted. The reason is because actually this SSL protocol it's just the port. Well, that's a computer screen, black again. So it's not really using SSL encryption. This is AOL instant message. It uses the port 443 for its traffic. Why it doesn't use its own port instead of using another service port? Because it wants its instant message to go through most firewall. But many firewall, they only open port for web traffic. They do not open port for other unknown port numbers. So, this is a reason that for IT security stuff, you should check all the web traffic and also HTTPS traffic, because it's highly possible that on HTTPS port, the traffic is not really related to web server. The traffic is generated by some other third-party network application. They simply use that port for its service. They try to go through the firewall, but they are not related to web. So there is no packet labeled as AMM, but there are many packets labeled as SSL. But if you check some of those SSL packets, you can see that they are not encrypted. This is because AMM is using this port. Wireshark understands AMM protocol, but if the port is 443, Wireshark would treat those as SSL traffic. So Wireshark will not try to understand those protocols. So we need to tell Wireshark that this port 443 traffic is actually following ARM protocol. Here, what I just say that many third-party applications, especially malicious software, they will use HTTP or HTTPS port for easy penetration of firewall. So even if you only open firewall port, it's not only open the web port. It's still not safe because attacker could use that port to go through your firewall. So we see a lot of SSL traffic from this is a client, this is a server, because this protocol means the server is the destination port. So this is a server. We find what's the IP address for the server. What does that remote IP address represent, whether it's a known server or not. We can use this so-called whois command to find who have registered with this IP address. If this IP address belongs to some well-known company, then whois command will tell you that this IP address belongs to a company. Because for any company, when they allocate, when they get some IP subnet for their own organization, that IP subnet allocation is a public information. So whois basically will check that information. You can use Kali Linux to do that. What's the IP address? Okay, so whois will tell you the information. So this is whois basically queries this public IP address allocation, those public database to find out that it belongs to this subnet, and this subnet belongs to this AOL MTC. So that is American Online. This is the actual organization. So from this net name, we know that it actually belongs to AOL company. And of course, the AOL company belong the organization name actually is this one. So you can use Kali Linux to do this checking, or you can just use some online quiz lookup service to do that. For example, this website, you can enter this IP address, and it will give you the same answer that which organization own this IP address, belong to this subnet and the AOL MTC. So from here, we know that this SSL traffic, we confirm that this SSL traffic actually is the AIM message. But we need to tell Wireshark that you should interpret this port 443 traffic not as SSL traffic, but as AIM protocol. So AOL has its own communication protocol, which is complicated if you don't know, but Wireshark already built in this AOL protocol in it, so it can understand it. But we just need to tell Wireshark that don't interpret that service as SSL, but interpret it as AIM. So how do you do that? You can right-click any one of those SSL packets. You choose this decode as to change its default configuration. So any one of those packets, right-click and decode as. So, this is port 443. This is port 443. How do you want to decode? So currently default is HTTP. So you can click and choose. So these are the drop-down menu. So all the protocol that can be understandable by Wireshark. Basically, Wireshark building all these protocols in its processing. AIM is one of them that Wireshark is understand. So you select AIM. Did I do it correct? Let me change the default. No, it's my operation is not. The response from this source to the destination, they should also be AIM. Okay, let me try. Okay, I think you need to change this. Originally is a TLS port, so you need to specify that TCP port, so it will be not treated as TLS. So you need to change this to be TCP port. You need to change its default and the understanding as AIM. After that, you can see that all here is changed to AIM protocol. Now it can interpret these messages as AIM. And now you can see this displayed information has been changed. This is a keep live. Originally, if this protocol is SSL, information is just continuous data because Wireshark will not try to interpret the data in SSL packet. Now it understand AIM protocol, so it will show what this message is about. This is messaging, acknowledge, this is messaging. So now it understands that. So we try to find the question one, what is the name of Ann's IAM body? So we try to find what username for Anne communicate with. This is messaging, and we can see this message. This is body. This is the body's name. So basically, this is the remote users that AIM message the Anne try to connect to. So that's the body name. And body name. So all these messages between Anne's computer and remote user is this one. So we get the answer for the first puzzle question. What is the name of Anne's IAM body? So this is the name. So you supply this answer. Then what was the first comment in the captured IAM conversation? So first packet is packet 23 is keep alive. Remember, the first message is actually keep alive, doesn't have any content. The second one is AIM message, and we can see the message here. This is to the body and message block. We can see this message, value message. So this is in this field. And so this is actual content of the message. Here, the secret recipe. So the whole thing is a message. So the answer to the second question, what was the first comment in the captured IAM conversation? Is this text, is a post text. Question 3, what is the name? What is the name of the file and transferred? So there are many TCP package with Anne's computer. So because AOL message is from Anne's computer to the AOL server, but when Anne try to transfer file to another user using AOL, the file transfer is between Anne's computer and the remote user's computer. It doesn't go through the AOL server anymore. So you should not focus on AIM messaging. So AIM message is just the message between a user and the AOL server. All the users, they send message to the AOL server to pass on the message. But for file transfer is the direct client-to-client transfer. The file will not go through AOL server. So we want to find IP address related to this Anne, and we know we can Google search to find what's the protocol, what's the port number used for the file transfer. So even though the file transfer will not go through AOL server, but the transfer still follows AOL's file transfer protocol. So if you do Google search to find AIM file transfer, you can find that it actually uses this port 5190 to do that. For example, AIM file transfer port. So you can Google search what's the port for AOL file transfer. You can see that this port is 5190. That is the port used for file transfer. Now we can focus on only Anne's computer and TCP like port. So suppose we don't specify source or destination. Is TCP port 5190. So that's the file transfer port. So all these packets is related to that. You can see this the SYNAC, set up TCP connection. This is the FINAC, so TCP closed down. So all these packets is actually related to that file transfer from Anne's computer to a remote IP address is 159. Anne's computer is 158. Remember that the remote user is on the local Wi-Fi, so its IP address is actually very close to the Anne's IP address. And so now we know what is the name of the file transfer. You can check this packet. Well, these are all. So we can follow. Let's see, follow TCP stream, and we can see that this transfer the entire data, and this OFT2 and cool file transfer. So that is a program used by AIM, and you can see the file name is a recipe.docx. This recipe.docx. So these are actual data. So what does OFT2 means? So you can Google search what does OFT2 means. OFT2. OFT2 file header, because it appeared in the beginning of that. This is OSCAR file transfer. It uses that protocol. What does it stand? It's OFT2 file type for the transfer. But anyway, from this, we can see that this is the file name for the actual data. And what is the name of the file? You can check the follow TCP stream. You can see that it's OFT2 file transfer protocol. The file name is recipe.docx. By looking at the binary or looking at follow TCP stream, you can see that. The file transfer is in plain text. That's why we can analyze it. So question 4, what is the magic number of the file you want to extract? What does the magic number means? You can Google search magic number. Magic number just means for any kind of file, the beginning few bytes for that file will represent what's the format for this file. For example, for PDF file, the first several bytes is always fixed. It will tell any computer that this file is a PDF file. For Word file, docx, it has its own magic number. If you Google search magic number file type, you can find like a Wikipedia page. These are the magic number for PCAP file. These are the magic number for the PCAP file. And so for different file, this first several bytes for that file will always be fixed to specify what's the file type for that. And many protocols can be identified by this well-known sequence of the bytes near the zero offset, basically the beginning, a few bytes. Almost all file formats have this header information. So those are referred as magic numbers. And for this one, if you want to extract the file, it's not so easy, straightforward anymore, because this is using this OFT2 file transfer protocol, but Wireshark doesn't build in understanding of the OFTP file transfer protocol in. For the question 2 example in the previous slide, because that file is transferred using HTTP, Wireshark understands HTTP protocol, so it is able to construct that file from HTTP traffic you can download. But for here, you cannot download it based on Wireshark, because Wireshark does not understand it. The file content exists in each part of the information. Follow TCP stream, we can actually see that, well, this this is a request, this is response. So this could be the actual PDF files content. Because if you see direction from Anne's computer to remote computer, so these are the Anne's computer's traffic to remote computer traffic. And so these belong to the first packet. And these actually belong to a second packet. So actual PDF file is here. How do you get it? There are a few ways to do it. This is called carve out. So you actually have the content for that file. It's just this content is split into many packets. You need to put them together. In addition, the packet content is not just about the file itself. It may have some communication protocol part. Like for HTTP, you always have HTTP GET or response header before the actual data. So you need to download raw data, then carve out the file content. You need to remove all these unrelated bytes in the beginning, in the end, only leave the raw data for that file down. Then you can recover the original file. We only have a few slides left. Basically, I will tell you how we can carve out using two different ways from the Wireshark. Okay, so I will finish the remaining slides in 10 minutes in next class. Any questions so far? Okay, that's all for today's class. Oh, remember, I have released the homework 2. Homework 2 is about Wireshark. Basically give you a network trace and ask you to analyze and answer those questions. The homework 2 actually is copied from the Dr. Donson's class in UC Berkeley. So it's the same project assignment, lab assignment as that. Okay, it is due next Sunday midnight. Okay, that's all for today's class. See you next time.
Hey, Professor, see you on Monday.